The first example problem we're going to do with our new equation for heat is going to be just what is the steady-state temperature distribution across the line. The line goes from 0 right here to length L over here, and at the left-hand side, the temperature is at T1, and the right-hand side, the temperature is at T2. One thing that's very convenient is to work in a dimensionless system. What does that mean? So, we can have many problems that have different L, for instance, L1 or L2, L3, etc. But we only need to solve the equation once, really. If we can somehow map this onto a new interval that goes from 0 to 1 using this conversion where x equals some dimensionless variable times the overall length of the system. So if we use this transformation, our original interval it goes from inclusive of 0 and the length L. Our new system, it goes from 0 to position 1. The question is, how does this impact the differential equation? So if we rewrite this differential equation, the temperature d time equals alpha del squared temperature del x squared. We're leaving q off for now. We can, I like to expand it just so that it's easier to see. Alpha del by del x of del temperature del x. So if we just simply take in this transformation, x equals psi times L, and you stick this relationship in for your variable x, we can recast this equation in the following way. Alpha del by del psi times L of del temperature del psi times L. But L in each one of these is a constant. And so you can pull the constant out of the derivative, and then you'll have this new equation, alpha by L squared, del squared temperature by del psi squared. So this essentially just absorbs all of the dimension into our thermal diffusivity. This makes life substantially easier. We have to update our boundary conditions. So t at position 0, comma t equals t1 is unchecked. But now we have t at position 1, comma for all t is now equal to t2 because psi equals x divided by L, and this position here corresponds to x equals L, which equals L over L, which equals 1. So now that we have this updated, we can just march through and solve our differential equation. First, let's do it at steady state, which means that the time derivative is equal to 0. Which also means that we're working in a total derivative because now temperature is a function of position only. It's now a single independent variable derivative. So this becomes the new differential equation that we have to solve. I already divided through by alpha over L squared because that is just a constant. 0 divided by a constant is still 0. So what we have to do, I made that too squiggly, is solve this equation by integrating twice. So it is as simple as it looks. First thing, separate variables. So you have d temperature, d psi equals 0 times d psi. So you integrate this, you get d temperature, d psi is equal to some C1. Okay, you do it again. Then you have, then you have dt equals c1 d psi. So you integrate it, and you end up with c1 psi plus a new integration constant, c2, is equal to temperature as a function of psi. So now all we have to do for the steady state is determine the values of c1 and c2. How do we do this? It's very straightforward. We use the boundary conditions. So the first one is that t at 0 is equal to, what would we call it, t1. So we put in c1 times 0 plus c2 equals t1, which means c2 is equal to t1. Now we can go back after this and solve for c2. The other boundary condition was t at position 1 is equal to t2. So we have c1 times 1 plus t1 equals t2, which means that t2 is c1 is simply equal to t2 minus t1. Okay? So then we put these two equations, these coefficients back in. We have the temperature as a function of position is equal to T2 minus T1 times psi, okay, plus T1. This is our solution in our new dimensionless coordinate. To go back to x, we simply put in psi equals x over L, and we can recast this into our original independent variable x is equal to T2 minus T1, all divided by L times x plus temperature 1. So solving it in the dimensionless system makes life pretty easy, especially when we get to the dynamic simulation solution, and it's easy to convert it back into the original independent variable x.